much for your presence in this session. So my name is Ricardo. I came from Nova School of Science and Technology and from the University of Lisbon, and the other authors are Ricardo, also from Nova School of Science and Technology, and Rodolfo Prieto from Warner Emission Systems. And it is my great pleasure to deliver this presentation with this time. Okay? So, this is a brief outline of my talk. I will present some objectives, then I will make an introduction, I will present materials and methods, then results and discussion, and finally some conclusions. So, on the left we can see the EGR, the exhaust gas recirculation system. Here you can see that the objective of the work is to determine the influence of the fin. The fin is this structure that is not present here in this picture, but it will appear afterwards. So the objective is to determine the influence of the fin to baffle distance, namely this variable d, in the temperature and stress distribution of a cooled EGR, and two materials will be considered. So the fin's length, as you can see, will range from 114 millimeters to 126 millimeters, and the distance d will range from 8 to 2 millimeters, as you can see. So, car manufacturers are facing now adaptations to the designs of their vehicles to meet the stringent limits of particle and the nitrogen oxide emissions, and regulations, as you can see here, are becoming increasingly strict to combat the amount of greenhouse gas emissions emitted from road transport. And in last week we had heard about the European Commission and the Parliament that they intend to not sell vehicles with combustion engines beyond 2035. So this is an important issue that will appear in the near future. About the EGR, how does it work? So the EGR is placed here. This is the EGR. So the exhaust gases that comes from the combustion chambers, part of them will go into the EGR. It will be cooled. It will go here. They will mix with the inlet air that comes from the intercooler, and they will enter in the combustion chambers, and the content of oxygen will be lower, the temperature will be lower, so the nitrogen oxide emission will be lower. So this is one of the hypotheses to lower the NOx emissions in the cars. So about the EGR that was simulated and studied, here you can see the subdomains. On the left, you can see the subdomain of the exhaust gases, and on the right, you can see the subdomain of the coolant of the EGR. So the process or the service parameters that we have defined in the computational fluid dynamics analysis that we carried out were summarized in this table here. So for the gas, for the exhaust gases, we define the pressure of 2 bar, a flow rate of 50 kilograms per hour, inlet temperature of 650 degrees, and for the coolant, we have defined the pressure equal to 4 bar, a flow rate of 1.5 cubic meters per hour, and the inlet temperature of 90 degrees, and the thermal efficiency for the system equal to 90%. So now you can see the fins geometry inside the EGR. It has this configuration. On gray you can see the solid, on blue you can see the fluid that was defined, and we divided the domain by cells in order to make the computational fluid dynamic analysis that we have carried out. So just to see the numbers, here we have the numbers for the fluid cells, for the solid cells, for the boundary layers in between the solids and the fluid, and the total number of cells that varies depending on the fin's length and increasing from 6.8 million to 7 million, more or less, number of cells in this analysis. Also, after the computational fluid dynamics that were carried out, we have made some thermomechanical analysis with the parameters from the computational fluid dynamics. And here you can see one example of the meshes that were defined. And as you can see, the number of elements also ranges and are lower for the shorter, thinner length, and higher for the longer, thinnest length and it ranges from 4.7 million to 5 million, more or less, like this. About the boundary conditions in the thermomechanical analysis, we have defined that these flange in these bolt-through holes were fixed in order to avoid the rigid motion of the system. About the materials that were used, we have considered two types of materials, namely an austenitic stainless steel, ISIN 304 low carbon stainless steel, and the ferritic stainless steel, 445 and 2 stainless steel. And those properties are in this table. As you can notice, the ferritic stainless steel has higher mechanical properties than the austenitic stainless steel, as you can see here. And the other difference that is very important is the thermal conductivity and the thermal expansion coefficients. So the ferritic has a higher thermal conductivity coefficient, which means that will dissipate more easily the heat. And about the thermal expansion, you can see that it is lower than the austenitic, which means that the induced stresses in the ferritic stainless steel will be lower than in the case of the austenitic stainless steel. So this is one example of the trajectories that we have determined for the computational fluid dynamics. Here you can see the inlet temperature at the gases, the exhaust gases, and here the exit of the exhaust gases, and on blue you can see the trajectories of the particles of the coolant. Going to the results, so for the 304 low carbon stainless steel at the entrance, we have a temperature of 650 degrees, more or less. At the middle, we have 458 degrees, and at the exit, we have a temperature more or less of 293 degrees. And as you can see, as the fin length increases, then the exit temperature of the exhaust gases will diminish. As you can see, it will go from 280 to less than 270 degrees, okay, something like that. While the coolant does not change very much the temperature with the fin's length increase. About the thermomechanical stresses, we have two critical locations, namely on the right and on the left. On the right, we should not make too much attention in this because, as I told you, here we have defined fixed boundary conditions, which is not really the boundary conditions that are in the structure. But by doing this, as you can see on gray, we have the maximum stresses that we have defined for the structure, 150 megapascal, which is more or less the yield strength at 600 degrees, like this. And on the, on the left, we can see the thermomechanical stresses that are induced and are higher than 150, and that exists on the baffle, as you can see here, and also in the entrance of the fins, as you can see here. So this is important here. Looking in more detail, we can see that those stresses occur in the baffle and in the fin at the entrance of the fin, and ranges from 250 megapascal, and it could attain 400 megapascal, like in the fins, in the curvature, in the stress concentration parts of the fins. And considering a cycle defined by the hot stage and the cold stage, and using the Coffey-Manson incubation and the parameters for the Coffey-Manson incubations, we have determined for the different fins with the different lengths, we have defined the amplitude stresses and the mean stresses, and we have determined the number of cycles till failure that are estimated for each configuration. So you can see that for the fins length with the shorter distances, the amplitude stresses are lower, the mean stresses are lower, so the fatigue life is higher, and for higher fins length, then we will have lower fatigue lives. Of course, the EG air functioning depends on the type of conduction. So we can have conduction in a city or in a highway, and the temperatures will be different, of course. And we have defined for the choosing of the fins length that we will apply 3 cycles per day, 365 days per year during 10 years. This is more or less 11,000 cycles during the service period, which means that the configuration that is better suited is this, with the fins length equal to 150 millimeters, with the number of cycles near what we want, okay, for the EGR. Looking at the ferritic stainless steel, we can see that the inlet temperature is more or less the same. The temperature in the middle is lower, and as you can see, the temperature in the outlet is lower than with the austenitic stainless steel, because this will dissipate more heat than the previous one. And also, the stresses induced in the structure, in the baffle, and in the entrance of the fins are more or less 70 megapascal lower than the obtained for the austenitic stainless steel, which means that using this EGR with the ferritic stainless steel, we will have higher fatigue lives and better performance. Now, looking at the exhaust gases and also to the pressure inserted by the coolant, we can see that for the exhaust gases, the stresses are very low, for the coolant also the same, and the maximum stresses that are applied are in the order of 10 to 12 megapascal, which are very low when compared with the thermomechanical and the thermal stresses induced in the system. Finally, another important thing is vibrations. So the motor, when it's functioning, for instance, this is a 4-cylinder motor with 4-stage motor, and considering 6,000 rotations per minute, this motor will induce a frequency of 200 Hertz, more or less. And as you can see here, we have placed in this axis the fins length from 114 to 126, and we can see that the variation of the first natural frequency will be like this, and the minimum frequency is 1190 Hertz, which is very far away from 200 Hertz, which will allow us to conclude that the system will not enter in resonance anytime. Okay? So to conclude, the gas temperature drop proves to be more efficient with the increasing length of the inner fins. However, thermomechanical analysis indicates that shorter distance between the fins and the baffle results in higher thermal stresses induced at the entry of the fins. Therefore, shorter fins prove to have a longer duration as a result of lower thermal stresses induced. The use of a ferritic stainless steel resulted in an improvement of the heat transfer process and in lower stresses of the overall assembly in comparison to the annealed stainless steel. The phenomena of resonance will not occur in the EGR system, and for a period of 10 years, when 3 cycles thermal per day are considered, the reference length of 120 millimeters for the fin should be adopted. Thank you very much for your kind attention.
Thank you for your very interesting study. Now we have time for a couple of questions.
Maybe
Yeah,
just a simple question. You have these fins which are more or less corrugated.
Yes.
Do you have coolant inside the fins, or
No.
they are just here so that the flow is not so laminar?
That's the intention.
Okay.
The flow is not so laminar. But
So
the
you have more
coolant-
heat exchange?
Yes, more heat exchange, but the coolant is all only outside
Okay.
the system.
Any other questions?
Okay. It's more a comment than a question.
Yes.
I really like the complexity of your analysis because you combine the CFD and finite element method, the flow and the material properties, and then the fatigue. So I really liked it. I really enjoyed it.
Thank you very much. Thank you very much for your comment and for your words.
I also follow my colleagues, so it's very impressive. Maybe it's easy to be in this side and make questions, and then because we are.
But I acknowledge every question.
Yeah, but
That's
just
fine.
two minor comments from my part, from my side. Maybe you have answered already that because we are always asking more, but you did very nice CFD analysis, then you did thermomechanical analysis, and you split both analysis. But about combination, you just said that, okay, I realize that mechanical stresses from pressure are low, vibration is not a problem. Maybe you have answer on this question. Can you comment?
Yes. So the induced stresses by the gases are very, very low, and also the stresses induced by the coolant. The coolant has some stress concentrations in one or two configurations for the fin, but they are very local, which it's not it could not be extended to all the domain. So typically the stresses are in the order of 10 to 12 megapascal, more or less, which is much lower than the 300 megapascal or 400 megapascal that are induced with the thermal stresses. They are not in the same order of magnitude. So typically what defines the fatigue life of this component is the temperature. The temperature for sure.
Yeah, and regarding that, you talk about Moore equation.
Coffee-Manson equation.
And if you consider the properties for the temperature, for the, I don't know what is the temperature in your case, but are you using the room temperature properties or high temperature fatigue properties?
Okay, thank you very much for the question. It's very difficult to find parameters for the Coffee-Manson equation for those temperatures.
Yeah.
And there's another difficulty because we have temperatures that ranges from 600 degrees Celsius to 300 degrees Celsius. So we have searched a lot of parameters and we have used those parameters for the Coffee-Manson. They are not applied strictly to those temperatures, but they make sense just for a first know of the fatigue lives that can be expected in this type of equipment. And by doing this, we determine we estimate some fatigue lives that we compare with the design requirements, and then we define a fins length. But we do not have the strict values for the Coffee-Manson parameters adapted for the specific temperatures in the EGR. Probably, I do not remember now the temperature for those parameters, but I guess it's not on the 600 degrees that we could be interested at the inlet of the EGR where the fins are more stressed.
Okay, thank you again for your presentation and for this session.